Good evening. Welcome to the regular monthly general meeting of the Tucson Amateur Astronomy Association. I'm Ed Foley, I'm the president, and we have tonight members here in the auditorium at Stewart Observatory at the U of A. We also have members on Zoom joining us, as well as members of the public streaming, and welcome to all of you. The meeting tonight, as usual, will be recorded and it will be available to your friends who weren't able to make it tonight. You can tell them it'll be listed on the website in the near future after we get things all uploaded. We have our crack tech team here tonight, but they are cross-training tonight. So good luck to each of you. That's right. Jim Knoll is crossing his fingers. I'm sure it'll go very smoothly. We've got some pretty tech-savvy folks. They just don't know each other's jobs, so that's great. We usually start the evening with a poem from our ex-president, David Levy. David, are you with us tonight?
Yes, I am. I'm right here.
Oh, excellent. Are you ready with some inspiring poetry for us?
Yes, I am. And last night, believe it or not, the sky was clear enough that I was able to get outside and get a look of the field of T. Coronae Borealis. It's still pretty quiescent, but I was able to observe last night, which brings me to the poem that I hope to read to you now. Is Robert Frost acquainted with the night? I have been one acquainted with the night. I have walked out in rain and back in rain. I have outwalked the furthest city light. I have looked down the saddest city lane. I have passed by the watchman on his beat and dropped my eyes, unwilling to explain. I have stood still and stopped the sound of feet when far away an interrupted cry came over houses from another street, but not to call me back or say goodbye. And further still, at an unearthly height, one luminary clock against the sky proclaimed the time was neither wrong nor right. I have been one acquainted with the night. Thank you, Dr. Ed, and back to you.
Thank you, David. Always inspiring to hear the words from the past telling us so much about what we all love. Another thing we love is presentations like we're going to have tonight. Dr. Laird Close is here this evening. Dr. Close got his PhD here at the U of A, and he is a professor here at the U of A. He's very familiar with this room. He has presented to us in the past. Now, Terry and Dr. Close both claim that. I don't remember it, so it might have been a couple of years ago, but welcome back, Dr. Close. His specialty is adaptive optics and infrared to boot. So he is going to tell us about one of our favorite subjects, and that is exoplanets. But his twist on exoplanets is he is looking at exoplanets being born. So very, very specialized, and I'm sure it could be quite interesting. And he has a little supplement because he is an infrared person and has noticed something about the night sky here in Tucson that he's going to share with us. So, Dr. Close, will you tell us about these stars with the newborn planets?
I'm going to try to, okay, there. I think everyone can hear me. Great. Well, thank you so much for inviting me to come and talk to DAAA. It's been a while, indeed, but I think some of the things I'm going to tell you about tonight, it's all new. It's all basically material that just has come out this year, so it's brand new, and it's really a pleasure to be here and share with everyone here. Such a keen group of astronomers. And so it's a little bit of a hybrid tonight. What we're going to do, we're going to touch on. I'm going to just trim this just a little bit. It sounds a little loud to me. How's that? Does that sound better? You guys can hear me in the back? Okay. Yeah, it's not too loud. Okay, good. So yeah, so what I'm going to be doing today is, just as Ed was mentioning, I'm going to tell you about some of the amazing work that we've been doing here a little bit about trying to understand how planets actually form. This is tricky. We know they do form, but we have very, very little in the way of actual observations to constrain this process. So this is important. And at some level, I'm going to show you some of the first baby pictures of planets. We know planets start off small and they get bigger, but we don't really know very much about that process. And it's important because if you want to live in a solar system that has habitable worlds like the Earth, this is the sort of thing that we need to understand. And then I'm going to pivot to a little bit of, I'm going to put my amateur astronomer hat on, and I'm going to talk a little bit about light pollution here in Tucson and some of the experiments that I've been doing here a little tiny bit. And hopefully you guys can inform me a little bit about your experiences with light pollution here in Tucson. So that'll be a little bit of a fun thing at the end. But first of all, I kind of want to make sure that we're all on the same page here. So I'm going to share my screen here, and we're going to just have a nice little video that's put together by the Space Telescope Institute. And it's just, let me just make it a little bigger. Okay, so this is, I just want to be all on the same page in terms of understanding what I mean by star formation. So the way it works is that gas and dust collapse and form cores. These cores, right, which you can see here, oops, sorry, those cores will then have a little bit of angular momentum, and as that angular momentum, as the core collapses, that angular momentum will spin a star, the protostar, the remains of that cloud into sort of a disk. And you saw that disk-like sort of presentation there. And then you'll see that there's sort of these rings around the protostar. There's areas of high density and areas of low density of the remaining dust and gas. And what's carving out those channels are planets. And artists know this, and everybody who draws these pictures knows that, inside these gaps there should be planets. The only thing that's missing are any observations of actual planets in the gaps of these disks. So, like many things in astronomy, we have a really good story. We just don't have a lot of evidence of it. So what I'm going to do here is I'm going to stop this. And I think I have to actually stop share. I'm going to then pop back into sharing again and share. I'm going to go to a different window and start my talk here. All right, share this. And then from the beginning. Okay, so here we go. All right, so I'm going to make the laser pointer so that everybody can see it. All right, there we go. All right, so the sort of the situation that I'm going to be talking about here, this is a lovely artist illustration that was made specifically for this work, which is kind of great. And so this is what I'm talking about here. This is basically a formation of a planet. Now, by planets, I'm going to lean pretty heavily into the idea that I'm talking about Jupiters. Okay, so these are big planets, Jupiters or even super Jupiters, because those are the planets that are with today's technology, those are the ones that we can take direct images of. So it's very confusing, the exoplanet space. There's transiting planets, there's radial velocity planets, and there's directly imaged planets. So tonight, and I know a lot of you guys take amazing pictures, and I love pictures of outer space. We're going to be talking about taking photos of planets, and not just any planets, but planets that are actually forming, baby planets. So literally pictures of baby planets. And what that kind of looks like is, this is an artist's illustration, but this is sort of a conceptual idea of what it might be like. We know that a planet like Jupiter is made of hydrogen and helium, and so that hydrogen and helium has to come from somewhere. And so it basically accretes down, and by accrete, what I mean is falls onto the surface of the Jupiter. And so this sort of blue material that you're seeing here is streamers of hydrogen gas that are falling along the magnetic fields and collapsing onto this young planet. And this is kind of this is very cool. This is actually only even the artists. This is a brand new kind of picture. There's only one of its type out there. It was developed for this system that we discovered called WISPIT 2b. And this is sort of an artist's illustration of what that planet might look like. So the cool thing is, so the one thing that we all know about Jupiter and other gas giants in our solar system, they're mostly made out of hydrogen and helium. And so we know that when they were little, they didn't have that much hydrogen and helium. When they became bigger, they got more hydrogen and helium. So there's this process, this transfer, this accretion process, where the hydrogen and helium falls onto the planet. And if you think about it, this must be one of the wildest planets in the world to be on. If you were on the surface of this planet and you looked up, you would see waterfalls of hydrogen and helium gas streaming in from outer space, kind of like, creating these accretion sort of ovals, a little bit like the aurora borealis, because it's a sort of a similar process in some ways. You're following the magnetic fields of the planet. And, you'd have these waterfalls of material streaming in from the outside. Now, I kind of theorized that these things should exist in 2012, but nobody had ever seen anything like this. And it took us a long time before we were actually able to definitively take the first pictures of these. So how do you take a picture of a baby planet? Well, you use the fact that you know that they're made out of hydrogen. And most of you are familiar with the term H alpha, hydrogen alpha. It's a special line, okay, right here at 656.3 nanometers. And I'm going to call this H alpha, and I'm going to say H alpha a lot in this talk. H alpha is an emission line given off by the most common gas in the universe, which is hydrogen. And this is one of the strongest lines in the optical. So the cool thing is that when these planets are growing, when they have the hydrogen falling onto them, the hydrogen, when it hits the surface of the planet, stops, and it basically creates a shock. That shock means that basically all that gravitational energy gets converted into heat. That heat turns into a plasma. The plasma then glows at the light of H alpha. So if you're an astronomer, and everybody in this room is an astronomer, what you could do with your little telescope is you could put in a continuum filter at, say, 668 nanometers, and you could take a picture of a star. And then you could put in your H alpha filter, and you could take a picture of a star. And then you could subtract those two images, and you should be able to see just the H alpha light coming from the planet. This is the idea. So I'm showing you here theoretical images of what these disks should look like. These are not actual photos. These are simulations. And if you look carefully, you can see these little black dots. Those are the planets. You can't see the planets in the continuum line. But when you go to the H alpha line, boom, they just light up. And you guys, a lot of people in the room take beautiful pictures of, say, Orion, and you're familiar with the H alpha emission line. So we're using that same technique, but we're using it to tease out in these young forming disks, individual planets. So it's sort of straightforward, except the problem is the angular scale here is tiny, right? You have to find young stars, which are 120 parsecs away. And so that means that this scale bar here is sort of that's about 100 milliarc seconds, so a tenth of 1 arc second, 0.2 arc seconds. So this is all of the science that I'm talking about is inside sort of a quarter arc second tonight. So the hard part is you need a lot of angular resolution. So by angular resolution, what I mean is we need to make really sharp images. And we need telescopes that are bigger than what you can actually get in space. If you could have a 6.5 meter optical telescope in space, JWST is great, but it's an infrared telescope, so it doesn't work at H alpha. But what we've done is we've used one of the Steward telescopes, one of the University of Arizona telescopes built in the Mirror Lab. And here you can see it's called the Magellan Telescope. And we use this telescope and we build a special instrument called an adaptive optics camera. And this camera, by clicking a mouse, I can basically get the same angular resolution of this giant 6.5-meter telescope as if it was in outer space, with much less cost involved. This is complicated, and we need well, it winds up to be a lot of software. We have millions of lines of real-time software, and it's very complicated. Our instrument's called MagAO-X, and this is our team, mostly of graduate students in the Optical Sciences College or at Stewart Observatory, the astronomy department. The PI is Jared Males, and I think I'm here. And Jared and I have worked together on a bunch of projects ever since he was a grad student. And this is our current team, and they're all young, brilliant people. This is what the instrument kind of looks like. This is me for scale in the clean room. And so it's a camera, but it's about the size of a small car. And it costs a lot more than a small car. This is our controller for the camera. And obviously, this is very, very complicated. I'm not going to really go too much into the technical details, although I do love the technical details. But what I will show you is the classic adaptive optics on-off. And so what I'm going to show you here is what happens when we take, so every second we take 2,000 images of what a star looks like, and we know what a star should look like, and then we take a picture of it. A hint is what we're looking at the screen right now is not what a star should look like if you were, say, at the 6.5-meter telescope, say, with no atmosphere. So you're in outer space. But unfortunately, of course, there is an atmosphere above the Magellan Telescope in Chile. And that atmosphere blurs out the image. And so you can't see a planet around this star at all. It's just a blob. For those of you that care, this is about 0.6 arc-second seeing. So it is actually a pretty nice blob. But for us, this is horrific. So what we want to do is turn on the adaptive optics. We're going to 2,000 times a second, we're going to change the optical configuration of the camera to try to remove the actual blurring of the atmosphere in real time. So here we go. I'm just going to turn on. So we're just taking the adaptive optics is off, and then boom, we just turned it on. Yay! Isn't that great? I tell my students that this is about as close to magic as you can really get, because if you didn't know better, this would be just magic. And it really is still kind of magical when you're at the telescope and you're just turning the AO loop on and off, which we actually don't do a lot of because we're at the 6.5-meter. We just leave the AO on most of the time. So I'm just going to play that again. I'm just going to play that one. There we go. And so when we turn the AO on, this isn't a planet, but it's faint and it's kind of like what a planet would look like, and that's real. What the giant yellow arrow is pointing to. These other little dots are well-known calibration spots, so that we can kind of understand where it is with respect to the star. And then you'll see some rings around the star. Those are airy rings. And you'll see that the image is a little bit blurry. That's because the CCD is, we don't have our chronograph in because we're doing an on-off movie. And so we're getting a little bit of bleeding from the CCD. These are special types of CCDs called EM CCDs. But in theory, it's not very different from the CCDs that you would perhaps used on your telescopes. But now everybody basically uses CMOS. But anyways, long story short, these are very good images. So if you think about it in terms of arc seconds, these images are 0.027 arc seconds is our angular resolution. That's very, very good. Pretty much we're making about the sharpest images now. That's images, not interferometric fringes, but true images. We're doing about the best of anyone in the world right now. And the reason why is that we're working in the optical, because of course, and by optical, what I mean are wavelengths of light that are short enough that we can see with our own eye. Although this particular example is a little redder than that. It's 875 nanometers, but still, we're not using infrared cameras. We're working in the visible where it's sharper. The optics is really complicated. I don't really want to spend too much time talking about that, but here's the thing to think, just to remember, if you go all the way back to the science, the idea is we want one camera to work at H alpha. So this camera has an H alpha filter, and this camera has a continuum filter. And I split the light here with a special beam splitter. So all the H alpha light goes into that camera, all the nearby H alpha light, well, just outside of it, the continuum channel goes into that camera. And then in real time, I'm taking data and I can subtract the images and I can let the planets pop out. And so that's the idea. So the first system I'm going to introduce you guys to is the first system we found H alpha from. And we were the first team to discover H alpha coming from PDS-70b, and then later PDS-70c. So it's very exciting. So the way to think about these systems is you've got a star, and you've got rings of dust, and you've got gaps in the dust, and then you've got individual planets that are accreting. And those individual planets themselves have little rings around them. Sometimes we call them CPDs, circumplanetary disks. And so when we started this project, we built it all here, just on the second floor of this building. And we did it pretty much all with grad student labor and just me and Jared. And it didn't work very well at the beginning, which was not completely surprising in 2022. But by 2023, we were doing better. And we knew these two planets were there at H alpha. So that's why we're trying to find them at H alpha. And then by 2024, we had gotten the instrument running very well. And we were making very good images. Hopefully, you can see that around these green circles, there are these bright H alpha blobs. Everything else is noise. And these are real images. You know, this has not been, you know, sanitized by some PR agency or anything. These are real data published. And this is actually 5 years of data of taking images of PDS-70. And hopefully you can see here that this is the continuum image. Okay, so this is the image taken outside of the H alpha. And if you look in the green circles, you see nothing. The planets are totally invisible. But when you look at H alpha, you can start to actually see these bright dots. And this is the actual H alpha light from the planet. And now if I subtract this image from this image, I get what I call my ASDI image. And then you can see here, hopefully you can see pretty clearly where every year, year after year, we're detecting these two planets. But the planets, you'll probably also notice, are changing in brightness. Like this planet C is pretty faint, but then in 2024, it was really very bright, and then it got faint again. So, you know, for many of you, for most of humanity, this was actually really the first time we saw a planet change brightness dramatically. So this is very exciting results. So we're actually seeing a growth spurt in that planet that lasted like a year, and then it sort of went back and was quiescent again. And then the B planet, the other planet here, it was sort of bright and then got fainter, and now it's getting bright again. So it's really cool. These are very dynamic things. Here's a little movie. I'm going to show you just a little zoom in, a little movie of what this looks like. And I'm going to show you again, because let's face it, it took me 5 years to make this. So I'm just going to show you again because I like it and it took a lot of effort. In fact, I'll even just go back and do it one more time. So that's that's what it looked like in 2022, and then 23, 24, and then 24 is where we got the big explosive event on planet C, and then there we go. Now it's sort of getting more. Planet C is quieted down, and B is now getting brighter. But you can really see how dynamic these are. And you'll also notice that they're orbiting, right? There's clear orbital motion over those 5 years. And this is kind of what it looks like if I plot out that orbital motion. So we can see that they're changing in brightness. We can see that they're orbiting. This is very exciting. So PDS-70 B and C are like the prototypical. They're the first two planets that we found where we could actually see that they're growing. This is kind of my idea of what the system looks like. You've got the star in the middle. You've got the two planets. Each planet has its own little ring of dust and gas around it. And sort of like an artist's illustration might look something like that. And so this is actually what our data looks like. Can we see some light being reflected off of these circumplanetary disks? Well, maybe. If you use your imagination, you might, this is the real data, and then this is sort of the interpretation of it. anyways, you can kind of see that these, if you follow all these green arrows, you can sort of see that there's these dust blobs that we image year after year. This is kind of, again, what the scattered light off of the ring would look like. And it's not surprising that there would be rings of dust around it. So just the highlights, again, I'm just talking about PDS 70 here, is that we've seen the planets, we've seen the H alpha, we've seen the variability, we've seen that there's 2 planets, we've seen that they have dust, little rings of dust around them. So that's exciting. But there are other stars in the universe than PDS 70. So my graduate student, Jialin Li, she has discovered another similar system. This is the dust ring seen by ALMA, this big black ring, and then she's discovered this black, it looks kind of like a dark object, but that is the H alpha companion. And then here again, you can see the classic continuum. You don't see anything H alpha, you see this little blob, and then if you subtract the 2, the H alpha dominates. So that's another good example. But this is, I think, the most exciting young star in the universe right now. And I don't think this is actually such a controversial thing to say. This is an amazing object called WISPIT 2. And it was part of a survey done at ESO and with the VLT telescope, the 8-meter. And what you can see here is this is the first image that was taken of it. This is sort of the discovery image. And you can see a lot of beautiful dust rings. Okay, no planets yet. The planets were going to come later when we had looked at H alpha. So it was first, this is an image taken in polarized light, which shows you the beautiful dust structures. So there's the star in the center, there's a bright ring, there's a cavity, and then there's a bright ring, and then there's this beautiful gap here. But as you can see, the VLT couldn't see any planets in the gap. But we were like, oh, well, they were friends of ours. They said, go take a look at H alpha. And so we did. And we looked at H alpha, we saw this beautiful bright object in H alpha, and that exactly corresponds to that gap. And so we were able to have found the first time that, inside this gap, okay, so there's a bright ring here, there's another bright ring here, and then right in the middle of the gap, there's this beautiful bright H alpha planet. And that's just like what that illustration that I showed you earlier today is sort of pointing out. Not only that, but there's actually inside of the inner ring, in that cavity, there's another bright object, which is, of course, astronomers are really bad at naming things. We just have these conventions and we just stick to them. So WISPIT 2b was the first planet discovered, and then this planet is called WISPIT 2c because it's an inner planet, and it was the second one to be found. If we look at this with the ALMA interferometer, we can see this big dust ring. If we look inside the dust ring, we can see these structures and those 2 planets. We can use a special interferometer called gravity, and we can get the spectrum of the WISPIT 2c planet. And you can see this beautiful, cool spectrum of carbon monoxide, just like you'd expect. So this is very exciting. So both these planets are real. And this is kind of the beautiful LRGB 4-color image that I made. And, and it's just, I just think it's one of the prettiest images that you could see. There's the outer dust structure. Here's the dark gap. There's the bright WISPIT 2b inside the gap. And there's WISPIT 2c, the other planet that's carving out this dark cavity. And there's the bright ring between the 2 planets. And there I can sort of draw all the, and label it. But you can pretty much, your eye pretty much tells you what you need to know. And so it's a lovely system, and I really do think it's just amazing. And I can't wait to find out what we'll be able to do as we push to the next generation of telescopes. There's some other things that I'm going to skip over this part pretty quickly. We're pushing further. We're trying to look at more and more objects. That's more than you need to know. This is kind of where we compare. We're working much, much closer in than any telescope right now. We're doing chronography at these very short wavelengths, which allows us to look at very small angular separations, like 0.05 arc seconds is where we're finding objects. This is a smorgasbord of all the different disks we're looking at and all the different companions that we're seeing. In the future, we'll be using the giant Magellan Telescope, which you can see here, an artist's illustration, of course, and that will allow us to even work a little bit more closely in. These mirrors, all these mirrors that you're seeing have actually been fabricated here at the University of Arizona in the Mirror Lab. So that's exciting. And to really be able to, I think that the exciting science there, so we could pivot away from understanding what baby planets look at like, and we could actually go and we could look for Earth-like planets that are rocky in the habitable zone with the giant Magellan Telescope. But we still need an extreme AO system like MagAO-X. And because it's on the GMT, what we have now is GMagAO-X, which is the new instrument that we're working on. And GMagAO-X looks like this. This is our current design, and which we're working on daily. But light basically comes down from the telescope and then goes into a very complicated camera. This is the optical layout of the camera, and that's the lower table, upper table. I don't really want to go into all the details, but like this is PDS 70 done today with MagAO-X. But if we use the GMT and GMagAO-X, it would be just so much sharper. The planets would just basically be dots, and we'd be able to see planets within sort of 8 milliarc seconds of the central star, and that would be very exciting. These aren't Earth-like planets, obviously. These are still Jupiters, but we would also be able to do reflected light from Earth-like planets, and we'd be able to look for signs of life. And so that would be a signature event for humanity and everything else. But I'm hustling along here because I want to actually pivot from my young planet work to some light pollution work, which I think a lot of people in the audience will find really interesting. So if you'll, we can maybe just take some of the questions on this later. And so remember your question, and I'll take that at the end. And what I want to do here is change projects and go back to here and then there, and then, yeah, I've got to escape out of this. Sorry, it's just, it's still running the PowerPoint. Okay, there we go. All right, and zoom to the zoom. Okay, I can do it like that. Okay, and then here. All right, and then. Okay, so so now for something completely different, as they like to say. I've been in Tucson. I did my PhD here in started in 1991. And so if anyone's lived in Tucson since the 90s, you'll notice the light pollution's gotten a lot worse, which is unfortunate. Tucson's not the brightest city. I mean, we had for a long time was quite dark, but it's now become quite bright. Part of that reason is that the nature of light has changed, right? Basically now, instead of incandescent bulbs, we use LEDs. And LEDs are actually quite different from an incandescent bulb. Very different spectra. And as somebody who's interested in spectra, I was just sort of curious what that would have to do with light pollution. So I guess I'm asking myself, like perhaps, well, some of you are very keen amateurs and perhaps you live in dark sort of Bortle 3 or 4 skies, but most of us, and by us I mean humanity, lives more like 8, 9, 7, 6 sort of Bortle levels. I think my house is somewhere around a 6 or a 7, which is unfortunate, but it's just the way it is. And I was kind of curious, like, could I see the Milky Way? Could I get rid of light pollution if I looked in the infrared, the near infrared, instead of the visible? Because maybe it's darker there now than it used to be. So let me try to explain my process here. So one of the things that is curious about astronomy today is that the United States has built the Rubin telescope, which is single-handedly, when it gets running, and it's basically running just this month, it'll start finding 100,000 discoveries of new transient events per night. 100,000 new discoveries a night, every night. That's very exciting. Unfortunately, the telescope networks, the professional telescope networks that can follow it up, like Eon Plus, they're sort of on the order of 30 telescopes. So it's tricky when you're discovering 100,000 things a night and then you've only got like some 30 telescopes to follow it up. As everybody in this room knows, the amateur telescope community has started to produce extremely professional grade telescopes, albeit somewhat smaller in aperture, but there are far more amateur sort of like 8-inch and up, reflectors, refractors than there are the professional community. Nobody really knows how many amateur telescopes there are, but estimates range somewhere between 100,000 and 300,000 telescopes, which mostly stay in our garages. I'm certainly guilty of that. And in part, it's because the light pollution's not great at my house. So, I don't really want to use it all the time. But I was kind of motivated that maybe it would be interesting to see if maybe I could use some wavelength of light that got away from the light pollution. Okay, this is more of an astrophysics thing, but it's fun if you can use a small telescope to do follow-up of an interesting transient event. There's really interesting science, but if you wait too long, then the thing gets too faint and it's too difficult to follow up on. So there's an interest in trying to follow up faint objects. The sort of extreme limit would be like 22nd magnitude with a backyard telescope, which you absolutely cannot do in my backyard because there's too much light pollution. The other thing that's disappointing is that Rubin is in Chile, which is great for Rubin. It's a beautiful place. All the stuff I was just telling you about MagAO-X, it's also in Chile at the Magellan Telescope. So Chile's great. The only problem is if you want to do follow-up in the north, because that's where most of the telescopes are, you tend to be looking kind of to the south, and looking to the south in Tucson's not great. This is Tucson. This is kind of a map. I'm going to be showing you data taken near my house, which is in the foothills, and it's kind of, bordering around sort of a 7 or 8. So it's this sort of red area. Not quite so bad as where we are now, which is downtown Tucson. Okay, so light pollution. Honestly, not the most well-studied subject. It's very important for our community. And for the most part, the filter that most solves light pollution is gasoline, and the idea that you take your telescope, you throw it in the back of your car, and you drive to someplace dark. And that works for 99% of us. And you guys have some really nice dark sites, and that is an absolutely good way to get away. You go there during new moon, during dark time, you go to a dark site, you don't have to worry about light pollution. Problem solved. Well, that's true. However, it can be kind of inconvenient, as we all know, and you're kind of limited to when the moon's down. And if you're trying to do follow-up of interesting like supernovae that have been just discovered, it may not be convenient to drive all the way out to a dark site. It might be nice just to be able to set up your telescope in your backyard. But so the way light pollution used to work is this is a spectrum of a light polluted sky. And we used to have a lot of these high pressure and low pressure and sodium lamps, which were great for a bunch of reasons. But they're, unfortunately, one of the things that they did produce was a fairly strong infrared line. You can see here at, it was a doublet at around 819, 818 nanometers. And this put out a lot of power. And it kind of ruined the near infrared. So if you had light pollution in the visible, you also had light pollution in the near infrared. And so nobody would think that working in the near infrared, and by near infrared, I mean sort of 700 to sort of 1,000. So I'm not talking about thermal infrared. I'm just talking about what you guys can do with your CMOS detectors at home from 700 to about 1,000, maybe 750. All right. And you can see that there's a lot of light. However, these lights, these high pressure sodium lights, even though there's still some in Tucson, they are disappearing because they're way more expensive than LEDs. So LEDs are different. LEDs are adapted to our eyeballs. Our eyeballs cannot see those 820 nanometer photons at all. So that's just a waste of power and energy. LEDs, if you follow these green lines, are much more centered on where the human eye can actually see. So of course, it means that light pollution in the visible is unfortunately pretty bad because the LEDs are cheap and they're abundant and they're really pumping up the night sky. And they're actually adding a lot of blue light that we didn't used to have before. So the light pollution in the blue has definitely gotten worse. So, but on the other hand, in the near infrared, you can see that the green lines are pretty much just flat. The LEDs are not pumping out a whole bunch of power in the near infrared anymore. Incandescent bulbs, also a really good example, used to be very common, now almost absolutely don't exist. And they put out almost all their light into the near infrared. So again, no one would think the near infrared would be a good place to have low sky background. There's also OH lines. There's natural sky brightness in the near infrared too, but compared to light pollution, it's fairly minor. The real question here is that, well, you just have to go out there and you just have to, do the experiment. The other thing that has limited people working at, say, like 750 nanometers to, say, like 900 nanometers is that most of the detectors that you could get for our community were very insensitive there. And so that was a problem. However, in part, and it took me a little while to figure this out. So if you're a company like Sony, which seems to have just black magic, the way that they can produce modern CMOS detectors, how many people here in the room have a CMOS detector for their telescope? Raise your hand. I just want to get a feeling for it. Yeah, so like most of us, right? A few people will still have CCDs. They're still good. Nobody will probably be using, but I mean, if you're using like a digital DSR, then you're also using, of course, a CMOS device and everything. And one of the interesting markets for Sony is basically for dash cams. And it's not really obvious that dash cams would be a huge market, but they are. Maybe not as much in the United States, but globally, dash cams are a very important market. You want a very sensitive detector that can run very quickly. Doesn't have to be very big, okay? So relatively, like a 4 megapixel device is all you need. Relatively inexpensive. But weirdly, also, it's nice if they work in the infrared, because most of the time that your car gets smashed into when it's parked is when it's dark out, and people want to have dash cams that can record that. So Sony has these very near IR sensitive devices. And I don't know if you're used to looking at these QE curves, but this particular device, which I'm going to use for my talk, for the rest of the talk, is the 585. And the IMX 585 chip has this beautiful, strong like QE curve. Sure, it's going down, but 38% of the light that this detector can detect is past 750 nanometers, and that's much better than what detectors used to be like. So, and it's also fantastic in the optical too. It's just a wonderful little chip, and I think a few folks, maybe even in the audience, have the ZWO ASA SI 585. Anyways, so I just wanted to look at the sky with it. That's it. I didn't really want to image anything but the sky, so I just wanted a big field of view. I rigged up something. It took a little bit of time, but I rigged up something with a wide field fisheye lens. And then I just gave myself a little filter tray here that I could pop in between a near IR filter and just a visible filter. And I just used a 750 long pass filter. So in other words, when I say near IR, what I mean is I put a filter in that passes all the light from 750 nanometers to 1 micron. At 1 micron, even the Sony device doesn't really, it's completely transparent, so it doesn't detect any more photons. So all CMOS devices are limited there. Obviously, this is the light pollution kind of profile from my house. And so what I'm going to show you here is, this is the prediction by light pollution app, which is a great app. And that's kind of like what the night sky looks like with my viewer. I managed to get a 40 by 70 degree field of view onto my detector, which is a pretty good field of view. It's not quite an all sky camera for sure, but I wanted to have some angular resolution too. And then, sort of, this is kind of tracks with the sky brightness as you go down. So there's the roof of my house, if you want to orientate yourself, you know, just a few degrees above the horizon. There's the roof of I'm in my backyard by my pool, just looking kind of to the south. And I'm kind of looking at the Milky Way here, which you can maybe there's something there. But then if I switch to the infrared, it's much clearer, much darker. The Milky Way just jumps right out. Honestly, when I first took this picture, I was like, holy crap, like that was amazing. Like I can actually see the Milky Way right down to my roof. And I thought this was very exciting. So, you know, it was a rare moment where it's like, oh, wow, that actually worked better than I thought it was going to work. So this blue light is the visible. So that's kind of going from 0.4 to 0.7. And then I'm going from 0.74 to 1 micron in the near infrared. And that's this sort of red light. So to be clear, I haven't been playing any games here. These images, it's less sensitive. The total QE is less, but the sky is much, much darker. As you can see, the sky is 10 times darker looking up, but looking down towards kind of higher air masses where you might be doing follow-up for Rubin, the sky is like, you know, almost 10 times, you know, 7.5 times darker. And at very low air masses, it is a factor of 10 times darker. A factor of 10 in sky brightness is a big deal. It's really great if you can have a darker sky by that factor, whereas in the visible, it's just like you're looking right into the muck. And we all kind of know that. And I was kind of curious about like, well, what does it really look like on a star-by-star basis? I'm zooming in now so you can see the individual stars. So that's kind of like what it looks like when you are in the near infrared from my house, and that's in the visible. And, you know, and now a lot of you are saying, well, okay, yeah, but some of those stars are just red, and so they're going to look better in the near infrared. That's absolutely true. So what I was sort of interested in doing is just finding, because I'm looking pretty much all the stars in the southern sky. So I just found some that were actually intrinsically blue, some A stars that had intrinsically blue light. And I just wanted to see, like, were they easier to detect using an infrared filter than an optical filter? Obviously, the red stars are way easier to detect with the red filter. Like, say, this little group of 3, you can see how he's there in the infrared, but in the optical, absolutely nothing. But those are pretty red stars. So, okay, that's not maybe, you know, that's very helpful if you're interested in red stars, but if you're interested in blue stars, not as helpful. So here's a nice blue star, HD, what is it, 172142. And, you know, pretty well detected in the infrared, but in the optical, not detected at all. And to be clear, these are both 10-minute images, you know, exactly the same amount of integration time, taken one right after the other, same scene, everything's the same, except that I can detect it in the infrared, but in the visible, there's just nothing. All right, so I'm running out of time here, but I just want to say also the moon, you know, moonlight is scattered light. A scattered light is Rayleigh scattered, so it's blue. Moonlight's actually fairly blue. So I did an experiment in moonlight. So here you can see again, now I'm looking sideways. There's the roof of my house. You can see, you know, look kind of like a roof of a house lit up a little bit by moonlight. And then when I switch to the infrared, this is really cool. Boom, that's what it looks like in the infrared. I suspect this is what the Milky Way looks like over everyone's house in this room, unless you live in downtown Tucson. There's just too much light pollution. But if you live just outside of downtown, this is the sort of image you can take of the Milky Way right over your house. And I think that's actually pretty cool. And, you know, let me just toggle back and forth there. So this is visible, which we're all kind of used to seeing, which is just, you can just see the brightest stars, that's it. And then whoop, in the near infrared, it's just the moonlight goes away, the pollution of Tucson. And to be clear, I live in the foothills, so I'm looking right at downtown Tucson on this shot because I'm shooting due south. So that's like right into the haze. You just absolutely can't see anything with the naked eye or with my camera, but I can. I did some experiments here, right here at the Stewart Observatory, 21-inch. So that's just outside those doors. And I did the same thing, the same camera. I built a little telecompressor for it, but this is an image in the visible, and this is an image in the near IR, near Deneb. And, you know, basically way more stars are visible in the near IR. I looked at some galaxies. I did NGC 7331, particularly beautiful galaxy, and I just removed the stars, and here I added the stars back in again. And it was really great in the near IR. In the visible, we just couldn't even see anything because the light pollution here is terrible. So long story short, when you add it all up and you do the simulations, this might be a fun takeaway for this group. What I feel is that based on my observations, that I could take an 8-inch and with a 585, okay, so lower QE but still decent QE in the near IR, my 8-inch should be able to get to a 22nd magnitude star in that filter in about I think it was running here. My integration was an hour. And, which is, a fair bit of time, but people here have probably integrated for an hour. And then over here, 100 minutes, sorry, 100 minutes. And then over here, if I do 100 minutes with a 24-inch, I will also get to 22nd magnitude, but I will be, choked by all that sky background. So I need the 24-inch to be able to get the same signal to noise as the 8-inch if the 24-inch is in the visible, because it's really being hurt by that. I think I'm basically simulating my house here, so like a Bortle sort of 7 sort of level, all right? And it's just basically that factor of 7.5 brighter sky in the visible. It's just killing the larger telescope. So it's kind of an interesting thing. And, I'd love to talk to people if people are excited about trying. To be clear, all you need to do is to get your nice telescope that a lot of people here have, just, buy, a $60 long pass, filter. There's a bunch of them that you can just buy and pop it into your rig. The focus is going to change, so you got to change the focus, of course. But and that's easy enough to do. You just change the focus, and you should be able to make a pretty good image. And it'd be interesting to know if you go deeper on the point sources. So that's kind of an interesting point. All right, so basically, this story only works now because we have these like good near IR QE chips coming out, the new CMOS chips. Long story short is that if you're in sort of a Bortle sort of suburban sort of situation, you can get 8 times fainter skies if you just switch to that longer wavelength filter. The moonlight that I was playing around with, that was a 3-day-old moon, so not a very bright moon, but even still, it even made it worse in the visible and better in the infrared. And then, so the main point is I'm thinking that an 8-inch can be competitive with a 24-inch when you're in a light polluted area. Now, obviously, if you're in a non-light polluted area, the 24-inch screams the 8-inch, obviously. But because the light pollution really makes that 24-inch work much harder in the visible. So, I mean, I think that's because everybody knows that, an 8-inch is something fairly decent and fairly easy to work with. A 24-inch is that's a serious rig, and that's a lot more work, a lot more expense. So it'd be kind of cool if we could, in our light polluted backyards, use 8 inches and do as well as a 24-inch. All right, so that's basically what I wanted to talk about. Sorry, I ran a little long there. Sorry, there was a little bit too much material to cover, but that's all I really wanted to talk about. So that's it. Thanks. All right. Well, I think
All right, you'll take questions on part A and part B at the same time?
Yeah, sure.
Okay.
Yeah.
Do we have any questions in the room? Here's Brad. You want to help me out? You want to get the side and I'll get this side?
Wow, I'm impressed. Getting down to a 40th of an arc second from the ground in the optical. Whoa. On the Magellan Telescope, what sort of magnitude limit do you have for detection?
Right.
And well, another question after that.
Oh yeah. So this is a great thing. So the point is, yeah, it kind of looks like magic, but we need a decently bright star to guide off of, is our to wavefront sense from. So we can get down to the star, the science that I was showing you, we're all done on sort of 13th magnitude stars. Now, 13th magnitude probably sounds really bright to everyone in the audience, but we're very proud that we can get all the way down there. We're counting individual photons, so all of our devices use these EM-CCDs, and there's electron gain CCDs. They have a read noise of 0, basically. So we run them at 0 read noise, and we run them at 2 kilohertz, and they count individual photons. So anyways, to answer your question, we can get to 17th magnitude on the central star. The planets, though, are really quite faint. In H alpha, the planets are about 22nd magnitude. So we're detecting 22nd magnitude objects that are located, 100 milliarc seconds away from other stars. That's about a factor of 10,000 times fainter. So it is all pretty great, and it is exciting. It is pretty unique. This is the only instrument that can do that kind of work. So we are very excited about it. However, it's not quite enough horsepower to find life on rocky planets or anything. We're still looking at Jupiters. Yeah.
Nice. You've been highlighting applications to exoplanets. What other applications are there that your colleagues are demanding to use your instrument on? For example, what if you look at Nereid to look for the binary companion? What can you do other than exoplanets?
Well, yeah, I mean, so that's a great question, and there's a lot of things. So it's basically anytime you have something bright, like the central star, and then something faint around it. So you could certainly find brown dwarfs. You can find low mass companion stars. You can look at those dust structures that to me are noise, but to other people are their science. There's even the idea of satellites. You can look for a bright satellite that maybe, and by this I mean an Earth, like a man-made satellite, and you can look for a fainter satellite going around it, which is of interest to some people. And you can also look at asteroids. You can find moons that are around other asteroids, and that's also some work I've been doing. And so that's kind of, and then we're just limited by the telescope time that we can get and our imaginations. But it's not really good for galaxies. So a lot of the fun work that a lot of people do, it's not really appropriate for that. That's where you need HST and JWST. That's where they do so much better than we do. But we can do really, really well on things like exoplanets and things like that. So, like everything, there's everyone has their strengths and their weaknesses, but
I'm very curious to know what your trade-off study was with an EMCCD versus a SPAD, and then how you went off characterizing the EMCCD before you put it into your system.
Oh, yeah. So to be clear, the SPADS arrays were developed a little bit later, at least for the commercial level. And those detectors tend to be really good in the blue. But our objects, our dusty stars, are brightest at around 1 micron. So it's a bit of a mismatch for us. They're fast. They're basically photon counting. So those detectors are powerful for that. But for this sort of science, it doesn't really work as well, because most of the astronomers that use these, they want to work at sort of a little bit of jargon, but I-band, the so-called the classical Johnson I-band is where we do most of our sensing. And SPAD arrays are not actually that sensitive there. And so the EMCCDs are the better choice. But they're both great technologies.
I have one for both lectures that you did. The first one was the 656.3 hydrogen filter. Because you said that you can see down to the 13th with the first hydrogen filter magnitude, and then of course the stars that you can pick up at 22 magnitude. So where would you find the 656.3 hydrogen filter?
Oh, what company?
Yeah,
Oh yeah, sure. It's a great company. It's
Alexa?
Alexa, and
Yeah.
I mean, you know, they're not so much for the amateur community. My particular filter was, I think, 2,500. But so it's a 1 nanometer wide filter. So for those of you who like H alpha filters, you might have an 8 nanometer at home. You might, if you spent a lot of money, have a 4 nanometer. But you know what we're using is a 1 nanometer. But you know,
Yeah.
a single night on the telescope costs $40,000. So spending $2,000 on a filter is not
Yeah.
wild, right?
Yeah.
But Alexa is an amazingly, and the throughput's 95% and the bandwidth is 1 nanometer. So again, kind of magical. It's really a beautiful, and it has no ghosts. It's really a lovely filter. I mean, it's for professional filters, Alexa is, or if you're a really, really serious amateur, which I know some of you are, it's a great company, you know, but again, it is very expensive. But yeah, no, over the moon happy with it.
And then your second lecture about the sky pollution, because they're saying a lot of things that I've been reading from different, from different companies, like, anyways, they're saying that the red light isn't the way to go, that the amber light is more effective to keep your dark eye.
Oh yeah.
The
Oh,
thing
yeah.
between, I forget, I think it was 900, was it millimeters or not millimeters?
Nanometers?
Yeah,
Yeah.
nanometers or something, or
Is this, so you're saying like whether it's better to use like a red light to keep your dark adaptation, or whether to go
they were
amber?
saying to use the amber, lights instead of the red lights to keep your
Yeah.
dark adaptation and that.
Right. So honestly, I don't even really know. I'd heard that too. I used to think that my little red light flashlight that I used was
Yeah.
really good. But then somebody told me that it actually doesn't really work that way, and it doesn't really matter.
Yeah, but
But
there is a certain,
I know nothing really
certain
about that.
parameter. There is a certain parameter, and right now suddenly I just forgot what the parameter was. Like 600 to 900, something like that. Ultra something,
Yeah,
that they had to stick within.
I don't know anything more than anyone else here about the response of the human eye. It's not really I mean, I wish I knew more, but I don't really.
Hi. So, long path filter, 750 nanometers, real cheap. Say I go insane or have been drinking and have been on the Thor Labs website and decide to buy a notch filter that cuts off at 0.3 and cuts on at 0.75. What's your thoughts on that?
Oh, you mean to just try to notch out the visible?
Yeah.
Yeah, I mean, sure. You could do that. The thing that's kind of crazy about LEDs is how blue light pollution has become. It never used to be blue. So this used to be what light pollution looked like. So a little bit, but almost nothing out here. Now with the LEDs, you do have stuff coming out here, but you're right. You could kind of notch all of this out, and then you'd be able to see some blue. Although the atmosphere itself isn't great. You're almost in the UV at that point. I mean, the LEDs are unfortunately almost over the entire span of what the human eye can actually see now. But yes, you could, there's nothing magical. I mean, all I did was just kind of look at these plots, and then I just picked a planetary long pass filter that kind of cut on here. So my little experiment was just sort of picking the light from this point, if you can see my cursor, out. I thought that was going to be, if you look at these LED curves, there's really sort of nothing there. But you need to have a detector that has some horsepower there. But the good news is that, you know, Sony's starting to make CMOS devices that can actually do okay. So it's new. And the sky has gotten much darker at those wavelengths. That's also new. And so these are just, to me, they're new things. I don't know. So part of my worry was coming and giving this talk is that like everyone would raise their hands and just say, we know this already. This is the most obvious thing in the world. And so I was kind of nervous about that. But I've given a talk now at the International SPIE in Copenhagen a few weeks ago. And it seemed to be that, you know, and of course I've been looking at the literature. There's just almost nothing published about this. But I am going to put out a little paper about this now. But, you know, the fact that what I really just love is that when you just look at these wavelengths, you know, the night sky, oh, well, that looks terrible, but that's okay. Don't change the lights. But it really is very dark because just light pollution just doesn't really exist very much at those wavelengths in the near IR. Because we've just it's amazing what we've done, right? In 10 years, we've basically changed all of our light bulbs. And in that period, light pollution's changed. But no one's really reporting on it. And so, you know, I think, of course, it's sort of obvious, but, you know, I think there's going to be a lot of people talking about that. Those light pollution filters that you can buy, you know, they're basically garbage, right? They don't work at all. And of course, you can go to cloudy nights and everybody almost says the same thing. They were based on like sodium lamps and halogen and mercury vapor lamps and things like that, things that just simply don't exist anymore. However, they will still sell you these light pollution filters. They don't really work. I guess I'm kind of pitching a light pollution filter here tonight. I'm just saying just buy one of these long pass filters that people like to use for planetary imaging. And, you know, and just use a broadband and, you know, use a modern, one of these modern devices, one of these modern CMOSs, and you can actually go pretty deep, you know. Now, to be clear, I just don't want to confuse anyone here. If you go to a dark site and you stick with the visible, you're going to beat the infrared because in a dark site, looking up, the visible is going to win every time because on a dark site, if you look straight up and you're working in the visible, you get fewer photons of brightness, okay? Because the visible sky is darker naturally than the infrared sky. The difference, the whole point of my talk was light pollution. The light pollution is a lot better in the near infrared. In other words, it's much lower in the near infrared than it is in the visible. Another way of saying it is that light pollution's gotten a lot worse, unfortunately. And so it really hurts now in the visible if you're in a suburban sort of site.
I don't see any questions in the room. How about Zoom? Who's got Zoom tonight in our tech staff? Bob's got Zoom tonight.
Doug asked, what gain and total integration times were you using for your near infrared images from your home with the ASI 585?
I wonder if I could just put that on the screen.
Are these just individual subs or is there a stack?
Yeah, so yeah, I totally have, let's see, oh, okay, whatever. Anyways, so the trick here is that they're 10 minutes, and I broke that up into I was doing 10 seconds, I think, in the near IR and 5 seconds in the visible, and then I just basically used Deep's ASI deep stack to just basically stack the images. And of course, I had enough stars because I had pretty much every star in the southern sky, and it was able to do a nice job with stacking the images. But this is kind of, I guess, important, is that Maybe I went really fast through this. Okay, like I had the tiniest telescope of everybody in this room. This telescope had a collecting area of about 1 centimeter. Okay, so because I was just using because it's a huge field of view, right, at Tondu. So I got my 40 degrees by my 70 degrees, but here, if you look carefully here, this aperture is, actually, do I call it out? Yeah, 1 centimeter, 1 centimeter effective aperture. So it's just a tiny little, what actually, it's a 4-inch lens, but when you have a 4-inch fisheye, your actual effective aperture is only about 10 millimeters. So because of that, I set the gain to 450. So in the ZWO controller, that's the high gain setting. So low read noise, very high gain, because you might think that I would saturate right away, but no. In fact, I really cranked up the gain so I could see the dark night sky with my 1 centimeter aperture. But it's all scalable, That's not a problem.
Doug also asked, what can you say about when the user should expect better results seeing for near infrared observing as compared to VIS? Is the seeing limited regime expected to be better for near infrared?
Oh, yeah. So, I think the answer there, it depends. However, if you're in a decent site, you should be able to get a slightly sharper image in the near infrared because seeing basically is better in the near infrared than it is in the visible. Now, this is not like you don't get a diffraction limited image necessarily. It's not a huge difference because it's just going as, I think it's basically it goes as 0.2, lambda to the 0.2. But you do get an advantage working. Probably everybody in the room might know this, is that if you go to a longer wavelength, the seeing kind of stabilizes a bit. But this is assuming that you're actually sampling the seeing. For my images, each pixel was 1 arc minute. Okay, so 60 arc seconds per pixel. So I wasn't really seeing the seeing at all. Even though my seeing was probably 10 arc seconds in my backyard, but I was still just had such a big field of view that I was basically putting a huge amount of sky per pixel. So anyways, yes, so it's another advantage, but I didn't really make too big a deal out of it, because it probably doesn't help a tremendous amount, but it doesn't hurt either to have slightly better seeing.
Okay. Chris says, considering the increase in sky light pollution due to future numerous satellites next 10 years, will astrophotography in the near IR help amateur astronomers?
Oh, what a good question. I was totally trying to think about that myself because I wasn't really sure. I think, sadly, I don't think it's reflected sunlight is mostly what bothers us when we take a long exposure and you see a satellite trail. It's that satellite acting like a little mirror and then sending sunlight into your detector off the satellite. So because sunlight has infrared light and it also has visible light, I don't think it actually solves the problem very well at all. I mean, if it's annoying in the visible, it's going to be annoying in the infrared too, at least in the near infrared part. It's maybe a little bit fainter, but no, unfortunately, I don't have a solution for that. I fear nobody does. It's a problem.
All right. Stephen asked, what about telescopes? Will optical glass in in corrector plates or refractor lenses block out short infrared wavelengths?
Right. So that's a really good question. So I could totally imagine most people in the audience might be like, well, sure, just go ahead and buy like one of these long pass filters, but maybe my glass totally like absorbs at that wavelength, and so I'll see no photons. And if you try to research, I dare you to do this for whatever telescope you have, whatever refractor, try to find the curve, the transmission curve from 750 to 1 micron. Nobody publishes these things. I mean, for the most part, Celestron and these companies, they don't like publishing any of this information. you have to go to cloudy nights and blah, 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 blah. But long story short, this is absolutely true if you go to 2 microns, if you go to 3 microns, 5 microns, very, very long wavelengths, most of your refractors won't work. However, what I'm talking about here is just red of optical, right? We're just going to the near infrared. And in the near infrared, almost every glass material that you have in your refractor will work just fine. In fact, some of them are actually clearer at these wavelengths. Things become more transparent as you go into these wavelengths, which is, by the way, why the QE dies, because unfortunately, not only is your optics getting more transparent, your CCD, your CMOS device is also becoming pretty much see-through. It becomes a piece of glass, basically. And so everything is transparent at these wavelengths. But the catch is if you've got very fancy like AR coatings on your optics, sometimes the AR coatings are designed to only work in the visible band. And so you can buy fancy optics at Thor Labs that work beautifully in the visible, but they will not work at these wavelengths at all because of the AR coatings, or they'll just reflect all the light instead of passing it. So that's a caveat that you got to worry about. But if you've got mirrors, there's zero to worry about for the mirrors. The mirrors are pretty much all aluminum. Aluminum works fine. There's a little bit of absorption at 800, which is unfortunate. But silver would be better, but nobody has silver mirrors, protected silver. But yeah, so it's something to worry about. The only thing that's kind of an issue is the focus. The focus has to change. So you have to refocus your telescope. You have to go out and look at a star and just focus on that star. But that's something I think a lot of us are pretty used to doing anyway. So, yeah, an AR-coated, a very special AR-coated optic might not work that well, but for the vast majority of telescopes and refractors that people have in this room, probably be just fine. Although I'd love to know about it. By the way, what I used there was a 13-element Canon lens that was made in the 90s that I bought for $50 off of eBay, and it's it was just a fisheye lens that Canon, yeah. Sorry. Actually, I bought one of those too, and that did not work very well. But that might have been the fault of the person who owned the lens before me. This particular lens, well, you can see a picture of it right there, but it's almost identical to the Rockin, but sorry, I'm not remembering right off the top of my head what it was. But it's a similar commercial wide field fisheye, so in other words, and with AR coatings on every surface, but it didn't matter. It was fine, the throughput.
All right, and we have one question and comment on YouTube. You've first got several love emotions or emojis, so that's good. And one says, wow, both topics were amazing. But there's a question from That's One Way to Do It. Is it possible to make near-infrared glasses for your eyes, or is it a matter of needing a long exposure?
For your eyes, like for the human eye? Oh, gosh. Well, I mean, our eyes, as much as I understand this, our eyes do pass these wavelengths because, again, we're not getting into the longer wavelengths. They are past. Our lenses do sort of focus them. And in fact, that's why if anyone does laser safety in the room, which I certainly worry about with myself and my grad students, sorry, so it's dangerous because you focus the light on the back of your retina, but the rods and cones in your eye and your iris don't actually, in your retina, don't see, for whatever reason, they don't actually really have a strong reaction to these wavelengths. There is some reaction, though. If you look at a really bright laser source, your eye can sort of tell that there's a slight difference. But do not do this, because the danger is, of course, is that all that heat is going on the back of your retina, and you can actually burn a hole in your retina at these wavelengths. So If you go to 2 microns, a wavelength of 2 microns, the chromatic aberration of our lens is so bad that we're not even focusing that light. And again, don't quote me on this, but it's a little less dangerous. It's still dangerous, but it becomes less dangerous. But a high-powered source at 800, 900 nanometers is extremely dangerous. And we treat those as like class 4 lasers, even if it's only a few milliwatts, because you just like a laser pointer, I can't hurt you with a laser pointer, because if I point a laser pointer in your eye, you blink, right? You're like, oh, you're dazzled. But there's no dazzle effect for these wavelengths, because you just simply have no response. But the heat energy goes in and it can be dangerous. So, but in terms of like, could you just like, wouldn't it be cool if when we looked up at the night sky, you know, it looked like this instead of like this? I agree, but I don't think there's any way with our CCD, our retinas just don't really see these photons at these wavelengths. They just don't. I guess they go right through. Our retinas are completely transparent, so we just cannot detect these photons. I don't think there's any. You'd have to change the retina. The optics are good. It's the retina that I think is the problem. As I
Would night vision goggles, the little
yeah.
binocular thing, that kind of would do something?
Yeah, you can do that, right? You can, that's sort of cheating, but yeah, of course, yeah, you could, you can, I mean, in a way, the Sony IMX 585 is like, it's probably better than a night vision goggle. It's probably more sensitive even, you know, so.
All right, that's it for the questions on YouTube. I will just follow up though with a comment that this is a great way to negate light pollution in Tucson, but the club does have a very nice dark site, Chiricahua Astronomy Complex. It's a portal too, so you can come out there and do visual all night long.
No, absolutely. Although the moon does come up there, and so if you want to go to a dark site when there's a moon, when the moon comes up, I mean, like, you know, you switch to the infrared.
We have plans for that, yes. Dr. Close, thank you very much. Okay, we're at the part of our meeting where we normally have our planet report. Dr. Eric Kokoschka gives the report at the meetings, and if you want to go back and refer to the information, it's also posted on the website on the landing page. So, Eric, tell us what's coming up.
I will miss the next 2 meetings, so you'll get the planet reports for the next 3 months, August to October. And so Mercury is right now in the morning sky, but only for a short time until the 17th of August. Then in September, it will go behind the sun and return in October in the evening sky, October 1st to 20th. But it will be very poor operation, so it won't blind you. Venus is, of course, the bright star in the evening sky, and it will get further down in the sky by sunset, so will be poor visible and then become invisible to the naked eye around October 10. And then it switches in front of the sun to the morning sky, and starting October 28th, it will be really good in the morning sky. The brightest that Venus gets will be minus 4.8 magnitude on September 18th. And so around mid-September, or around that time, it's so bright that if it's really clear sky, you can see it in the daytime, like you look at 3 p.m. up 40 degrees high and you see a little star there. Then Mars is pretty much rising at the same time, 1 o'clock in the morning, throughout the 3 months. Mars is orbiting so slowly that it really doesn't change too much. And by sunrise, it's pretty high up, especially by October. And its magnitude doesn't change too much either. It's first magnitude throughout the next months. But it moves in the sky from Taurus to Cancer during that time. Jupiter right now is behind the sun, so it's not visible. And then around August 11th, it will slowly come in the morning sky visible again. And so by October, it's still in the morning sky, but much better visible. What really special is about when you observe Jupiter in the telescope within the next year is that the satellites will be orbiting edge on. That means they won't go around the North Pole of Jupiter or South Pole, or so they really all go across the equator of Jupiter, and so they will eclipse each other or cult each other, and we'll have lots of interesting phenomena over the next 12 months. Not right now because Jupiter isn't well visible, but once it gets to fall and winter, then there will be quite a lot of interesting phenomena that occur really only every 6 years, and this year it's better than most other years. Then Saturn comes in opposition on October 4, and so it will be visible all night. Right now it's rising in the late evening. The rings are open again this year. Right now it's 9 degrees open. That's about a third of maximum, so it's still not too much. And then within the next 3 months, they go down to 6 degrees. So they are still somewhat narrow. Uranus is a morning up near the Pleiades. Won't come in the evening sky till later October. Neptune has a opposition on September 25. So that's when it's best visible in a binoculars or a telescope. Don't forget to watch the Perseid meteor shower. It's only 5 days away, the center of it. Probably meteors are already coming these nights if it's clear. The maximum is around the 12th of August. And that's the day of the total solar eclipse that passes right next to the North Pole and then goes south in Greenland, Iceland, and ends around Spain. And it goes so close to the North Pole that it's somewhat unusual because most solar eclipses, if you look the path across the world maps, they go from west to east. But this one starts in the east, then goes to the North Pole, and at 89 degrees latitude, what's called the southern limit is actually further north than the northern limit. And so it goes right next to North Pole, where when you look in all directions, it's south. So the directions don't make sense anymore, and then goes straight south through Greenland, Iceland, and in Spain in the evening. Well, it's 8 p.m., but the sun is still shining there. Well, there are probably lots of Europeans will gather there. For Tucson, what's more interesting is 2 weeks later, there's a partial lunar eclipse on the 27th. It's pretty much all evening. Once it gets dark, moon is just getting eclipsed, and it ends at around 11 p.m. So it's perfectly situated for evening observations. And 96% of the lunar disk will be in the umbra. So there will be just a little sliver that is still directly illuminated by the sun. The rest will be probably a dark red moon. That should be quite nice to watch on this 27th. Hopefully the monsoon's clouds are disappeared by then. We'll just see. Happy observing.
Thank you for that report. Terry, there's your answer on the eclipse too. Okay, that's it for the main body of the presentations, and we'll say goodbye to our friends on social media, I think.